Hi, welcome back. This is derivatives involving logarithmic functions, part 2. So this is my second video. I'm going to do a few more examples because we have to review a lot of stuff from Calculus 1 as we're working through these. So I wanted to give you lots of examples. In particular, the quotient rule is something that we haven't done an example of yet. So that's what we're going to do in this first example here. Okay, so example, find the derivative. Find the derivative. Okay, and, there we go. What we have here as our function for number 1 is y equals ln of 6x all over 6x. ln of 6x all over 6x. Now this one might look like it's easy, but it takes a little bit of work. The thing is, when you're dividing like this, and you have a variable on the top and the bottom and nothing cancels out, you have to use the quotient rule. And most people hate the quotient rule or dislike it. I'm one of those people because it's long and it's hard to remember. But it is the quickest way to do a problem like this if you remember it. Okay, so how does the quotient rule go? Quotient rule. Well, it applies when you have a fraction and you're taking the derivative. So if you have u over v quantity prime, this is equal to, let me make sure I remember it right, it's going to be vu prime minus uv prime all over v squared. Okay, so again, vu prime minus uv prime all over v squared, where u's on the top and v's on the bottom. And some people like to think of the top as the high and the bottom as the low, and so they think low d high minus high d low all over low squared. That's another way of remembering it. But just like the product rule on the last video, you do want to label everything, and then you're going to have to calculate your u prime and v prime somewhere over on the side, and then at the end you plug it all into the formula and you simplify. Okay, so like here, our numerator ln of 6x, that's going to be our u, and then our denominator is going to be v. So here v is 6x. And then somewhere over here on the side, you want to work out what u prime and v prime are. So let's go ahead and do those. Okay, so let's start with u prime. So u prime is going to be the derivative of ln of 6x. So that's a composite function. So we take the derivative of the outer function, inner left alone, and multiply it times the derivative of the inner function. So it's going to be 1 over 6x times the derivative of 6x, which is just 6. So we're going to have 1 over 6x times 6. Okay? And hopefully that's not too bad. So let me zoom out a little bit so I actually have enough room to write here. Okay, so we got 1 over 6x times 6. So obviously the 6's cancel out because this one's on the top. So that means our u prime is actually just going to be 1 over x. Alright, and then also we're going to need to calculate v prime. But fortunately v prime is pretty easy here. So the derivative of 6x is just going to be 6. Okay, so our v prime equals 6, because the derivative of a constant times a variable is just a constant. Okay, so now we've got our u prime and we've got our v prime, we've got our u, and we've got our v. So we're going to plug everything in here into the quotient rule. Okay, so we've got VU prime. So that's going to be 6x times 1 over x minus uv prime. So that's going to be minus ln of 6x times 6 all over v squared. So that's going to be all over 6x quantity squared. So once again, I'm just looking at this formula right here and plugging everything in. Since I have it all labeled, it's not so bad. So v is 6x, u prime, we said, was 1 over x, minus u was ln of 6x times v prime, which was 6, all over v squared, so all over 6x quantity squared. So we're good. That's our derivative, and we have to simplify it. Okay, so this right here is dy dx. Okay, so those x's are going to cancel with the 6x and the 1 over x. And then beyond that, there's not a whole lot to simplify here. But one thing we can do is we can factor out a 6 on the top. So if I factor out a 6 on the top, I'm going to be left with 1 minus ln of 6x. Okay, and then on the bottom, if I go ahead and square the 6x, remember that you can actually, as long as things are just multiplied together, you can distribute the exponent. So I'm going to be distributing the 2 to each of those exponents. So that would give me 6 squared times x squared on the bottom. And then 6 squared is, of course, 36. Okay, so we can, instead of writing 6 squared on the bottom, we'll write 36. And then dividing through, the biggest number that goes into both 6 and 36 would be 6. So we're going to divide the top and the bottom by 6. Okay, so after we do all that, we're just going to have a 1 on the top. So we're going to be left with 1 minus ln of 6x on the top. And then on the bottom, 36 divided by 6 is 6x squared. So our answer is going to be dy dx equals 1 minus ln of 6x all over 6x squared. Okay? So hopefully that's a good review of the quotient rule. Cool. All right. So now we have been doing the chain rule, but we haven't done ones that are difficult with the chain rule. So I wanted to do a little bit more challenging problem involving the chain rule. So for problem number 2 here, we're going to be doing the derivative of y equals 9 times ln of the quantity 3 ln of x. Now, if you're already familiar with the chain rule, this might be a piece of cake for you. But if you don't remember the chain rule, it could be confusing. So remember, with the chain rule, you work your way from the outside inward. So this constant here is not going to do anything. The 9 just stays there. But we do have a composite function here, ln of 3 ln of x. So we have to work our way from the outside inward, taking the derivative and working our way inward. So here our dy dx is going to be 9 times, well, the derivative of ln is the same as 1 over. Okay, so we're going to have 1 over 3 ln of x. So that was the derivative of the outer function, inner left alone. Okay, now we multiply this times the derivative of the inner function. So here the inner function is 3 ln of x. So what's the derivative of 3 ln of x? Well, 3 is a constant, so it just stays there. And then the derivative of ln of x is 1 over x. So we're going to have 3 times 1 over x. So if you are familiar with the chain rule, it's actually pretty easy. But it can be difficult if you're not sure how to work with the chain rule. So this is kind of a review of the chain rule. And if you need more help with it, remember this is called the chain rule. So it's basically just the same thing we did in the other video, where the derivative of ln is, the derivative of ln of u is 1 over u times u prime. Here our u is actually this inner function 3 ln of x. So we got our 1 over u times u prime. Okay, all right, and then we can just simplify this a little bit. So 9 times 3 is 27. Okay, so we're going to have a 27 on the top, and then on the bottom we have 3x ln of x. So we have 27 over 3x ln of x. Okay, and then we can simplify just a little bit, dividing the top and the bottom by a common factor of 3. We get our final answer, which is going to be 27 divided by 3 is 9 over x ln of x. Okay, so 9 over x ln of x is our final answer. So it's a logarithm with within another logarithm. And you could also have a logarithm within another logarithm within another logarithm. But, you know, that would be the same idea. You would just have to do the chain rule 3 times instead of twice. Okay. Okay, so what we're going to be doing next is we're going to do a couple examples of logarithms with different bases. So far we've only done natural logarithms. So just remember, there's the natural log, natural logarithm is where you have ln of x. And then you've got a common logarithm. Some people don't know about this one, but when they say common logarithm, that's actually written as log base 10 of x, except they don't write the actual 10. Okay, so a common logarithm on your a lot of calculators, instead of saying log base 10, it'll actually just say log of x. But that's a base of 10. It's assumed that it's a base of 10. Okay, so log of x or log base 10 of x, those mean the same thing. Okay, and then lastly you've got a general logarithm. A general logarithm, or whatever you want to call it. We could just call it a logarithm. So a logarithm with any base. So let's just call the base b. Well, that's going to look like log base b of x. Okay, so remember the base. The base is actually just this little number down the bottom right corner. So now common logarithms and logarithms with base b are going to both use the same formula. It's just with the common logarithm, the base is understood to be 10, so here b would be 10. Okay, so I'm just going to be covering the derivative of a logarithm with base b, since you can easily just apply that to log base 10. So what's the derivative of a logarithm with base b? Well, first of all, I'm going to try to make a little table here with these derivatives. So I think I'm going to zoom out a little bit more. Okay, so derivatives. Give me a second. Okay, so we already know that the derivative of ln of x is just 1 over x. So we already knew that one. So then what about the derivative of log base 10 or log base b? Well, it turns out that that one is almost the same as the derivative of ln of x, but you end up having to add in an extra factor in the denominator. Okay, so the derivative d dx of, for example, log base 10 of x is going to be 1 over x times ln of 10. So ln of the base. So this is going to be 1 over x times ln of 10. So basically, it's still just 1 over x. You just end up having to have ln of the base in the denominator. Okay? So for example, the derivative of log base 13 of x would be 1 over x times ln of 13. Okay? And so then in general, the derivative of a logarithm with base b is going to be 1 over x times ln of b, where b is the base of the logarithm. And of course, you can still use the chain rule with these, and you will be using the chain rule. There's only a couple of these in your homework because they're less common than the natural logarithm. The natural logarithms are really prevalent. They show up a lot. The other logarithms, despite their name, aren't used as much, but it's important to be able to do them. Okay? So it's just a slightly different formula. Basically, if you don't have a natural logarithm, you end up with natural log of the base in your denominator. But other than that, it's the same formula. Okay, so let's see another example. Well, a couple of them. These are generally not that challenging if you know the formula. Okay, so example. Find the derivative. Find the derivative. Okay, number 1. New example here. Let's find the derivative of y equals log base 10 of 7 theta. Find the derivative of y equals log base 10 of 7 theta. Sorry, I'm zooming in a little bit. Getting a little bit thin writing there. So, so here the base is 10, but we don't just have an x, we have theta. So here theta is our independent variable. So what we're going to be calculating here, instead of dy dx, it's going to be dy d theta. But it's just a letter. It's a letter just like x. That's our independent variable theta. But we are going to have to use the chain rule here. So it's going to be 1 over 7 theta, but because the base is not a natural logarithm, we actually have to have ln of 10 in the denominator. So what we're going to have here is 1 over 7 theta times ln of 10 in our denominator. So that's, using the chain rule, we also have to take the derivative of 7 theta and put it out front here. So what's the derivative of 7 theta? Well, that's just going to be 7. So we have 1 over 7 theta times ln of 10 times the derivative of 7 theta, which is going to be 7. Okay? So really, the rule we're using there with the chain rule is basically saying d dx of log base b of u, where u is a function of x, is going to be 1 over u times ln of b, where b is the base, times u prime. Okay, so that's just the same as the formula for the derivative of ln of u. It's just because the base is an e, because it's not a natural logarithm, we have to throw in this ln of the base on the bottom. Okay, so that's what we did here. So hopefully that's helpful. So with that, we could just simplify this a little bit and we're done. So these 7s cancel out. All right, and that's going to give us our answer. So our answer is going to be 1 over theta times ln of 10. Okay, and it's standard to write your variable first and then your logarithm. Okay, people usually write logarithms at the end when they're multiplying, just because it's easier to read. Okay, so that's going to be our answer, 1 over theta ln of 10. Pretty cool, huh? So those are not so bad. Okay, so I think I just wanted to do one more. Okay, so problem number 2. I'm going to zoom back in here. Problem number 2. Y equals log base 7 of x plus log base 7 of x to the 5. Y equals log base 7 of x plus log base 7 of x to the 5. Now there are a number of ways you can do this problem. But it's really up to you. One thing that you could do that would make this problem easier would be to go ahead and condense at the beginning. I don't know if you remember how to condense logarithms from pre-calculus, but if you're adding outside the logarithm, that's the same as multiplying inside the logarithm. So that might actually be probably the quickest thing if you remember how to condense. Okay, so I'm going to go ahead and condense these because they have the same base at the beginning. So when I say condense, I mean we're using what's usually called the product rule. So if you're adding outside the logarithm, that's the same as multiplying inside the logarithm. So like if you have log base b of capital A plus log base b of capital B, then this is the same as log base b of a times b. So adding outside the logarithm is the same as multiplying inside the logarithm. And the reason I'm going to do that is that way we don't have multiple fractions where we have to build them to a common denominator and all that. So I'm actually going to do this condensing before I take the derivative, just so that I don't have to deal with fractions as much. Okay, but you could also just take the derivative of each term, but then you would have to build to a common denominator and combine the fractions, which I think would be might be a little bit more work, but it's really up to you, whatever you like. Okay, so to condense here, since we're adding on the outside, we're going to be multiplying on the inside. So what we're going to get here is y equals log base 7 of x times x to the 5. And remember, when you're multiplying exponentials with the same base, you add the exponents. And if they don't write the exponent, it's automatically 1. So this is going to be x to the 1 times x to the 5. So that's going to be x to the 1 plus 5. Okay, so we have y equals log base 7 of x to the 1 plus 5, which is actually x to the 6. So we have y equals log base 7 of x to the 6. Okay? And then there's a couple of ways you can finish the problem. One way would be you could bring the exponent out front. You're allowed to do that. The other way would be to just use the chain rule. So either way is fine. But if you want to use stuff from pre-calculus, that can be kind of fun. So just for this one, I'll do some more stuff from pre-calculus. So here we can use the power rule. Okay, so call the power rule from pre-calculus. So here, remember that if you have log base b of a to the r, where r is the exponent, you can just bring the exponent out front. So that's the same as r times log base b of a. Or you can just use the chain rule like we did on the earlier problems. It's really up to you. Either way will work. One of the nice things about math is you can do the same problem different ways, and as long as you don't break any rules, you're still going to wind up with the same answer. Okay, but we'll just do that for fun on this one since it's not too hard of a problem. So if we bring the 6 out front, we're allowed to do that. We get y equals 6 times log base 7 of x. All right, and then it should be super easy now to find the derivative. Now, you didn't have to use all this pre-calculus. You don't have to use the power rule from pre-calculus and the product rule from pre-calculus for logarithms. But I just wanted to do an example of it just so you could see that some of that stuff in pre-calculus can be useful here. Okay, so now I'm going to go ahead and find the derivative. Okay, so we're going to take the derivative. Take the derivative. Well, since 6 is a constant, this is very easy to take the derivative of. We don't have to use any chain rules or anything. So the derivative of log base 7 of x is just going to be 1 over x times ln of 7. And then we still have a 6 out front. So we've got 6 times 1 over x ln of 7. And then if we move the 6 to the top, we get y equals 6 over x ln of 7. And all that pre-calculus I did, that was optional. I mean, you also could have just taken the derivative the way it was and then build them. You would have to build the fractions to a common denominator. But if you work through the whole problem and you do it correctly that way, at the end, after you get a common denominator and you combine them, you're still going to get the same answer. Which is one of the cool things about math. I always like that about math, that you can kind of take your own path. Generally, it's a good idea to take the easiest path you can find, but that's up to you.